Hello, everyone, and welcome back. Today we're going to begin our discussion of functions, which are an object that is central to almost every area of mathematics. Certainly you've talked about functions a lot in your calculus courses or whatever before, but as you're going to see, the sort of true mathematical definition of function is a bit different than the definition you're used to in calculus, in a few ways. One is that in calculus, whenever you talked about functions, it was always in the context of numbers. Whereas when we talk about functions mathematically, we're not necessarily going to be talking about numbers. We're going to replace that idea of numbers with an arbitrary set. Okay, so here's our definition in all its glory. We're going to be talking about a function whose name is going to be little f, uncreatively. Not going to change that part from calculus. If I don't have a reason to do otherwise, I'm always going to choose little f as the name of a function, or little g for a second function, and so on. And in order to have a function, we have to specify two sets. We have a set A and a set B. And what are we going to do? We're going to assign to every element of the first set, A, an element of the second set. And in fact, exactly one element of the second set. Hidden in this phrase, exactly one, is the other really key difference between functions in the mathematical sense we're talking about here and functions in the calculus setting you've talked about before. That's that in calculus, when we talked about a function, we talked about something having at most one output for every input. And so we allowed the possibility, for instance, that a function was undefined at certain points. We're not going to allow that here. A function must be defined at every point in the input set. That is what this is saying, basically. That is what this exactly one element here is doing. If that doesn't yet make sense, don't worry, I'll do lots of examples of how this differs from the calculus definition and show you all of those things. Before I hop all the way into that, though, I want to go ahead and talk a little bit about how we write these things down in terms of notation and what we call them. Usually, if we want to talk about a function f that goes from a set A to a set B, we'll denote that f colon A, and then an arrow, and then B. And so we'll read this as a function f from A to B. And so this arrow here is really the word to, if you read it in English. And in fact, the LaTeX code actually mirrors that exactly. Namely, it is just the backslash and then the word to. Now, in this arrangement, we have a name for the set A and a name for the set B. We name the set A the domain. And then we name the set B, and I know you're expecting me to say range, but for reasons that we'll talk about later, mathematicians tend not to use the word range, but even if a mathematician does use the word range, they definitely don't use it to mean the set B. Rather, mathematicians will tend to call the set B either the target or the codomain. In this class, I'm usually going to prefer codomain, but target is also a perfectly reasonable word for what this set is. We'll talk about that in a bit. Now, I'll note in mathematics, anytime you see the prefix co in front of a word, basically what that prefix is saying is like that, but the other one. And so the codomain, well, it's kind of like the domain, except it's not the domain, it's the other one. That's basically what co means anytime you see it. Now remember that what a function is doing is assigning to each element of A an element of B. So if f assigns the element B in B to the element A in A, we can express that in a couple ways. So one way we say that is we express it as f of A equals B. And this should be very familiar. This is reading exactly how we would have done in something like a calculus class. So f of A equals B means that if you take the input A, then you get the output B. The less familiar way, but the one that you'll also see a lot, is this, which will read as A maps to B. Possibly with an F above the arrow, possibly not with an F above the arrow. Now, one thing that's important is the difference between this arrow and this arrow. And it's important to get these two correct. So this arrow goes between two sets, describing a function's domain and codomain. This arrow goes between elements, describing an element of the domain and the element in the codomain that it maps to. And so the LaTeX code for this arrow is, in fact, \maps to. Here's an instance where the LaTeX code can help you internalize the difference between these two symbols. So I want to do a couple examples here that are very abstract. So I want to start with talking about functions from the set 1, 2, 3 to the set heart and diamond. And I've specifically here chosen heart and diamond just to emphasize these things don't have to have anything to do with numbers. They can just be symbols. And so the way I'm going to visualize what a function is really doing here is to draw a bubble here for the set A, that is for the domain, where I'm going to have a dot in the bubble for each element of A. So this dot is going to be 1, this dot is going to be 2, this dot is going to be 3. I'm going to do the same thing for B. B only gets 2 dots because B has 2 elements. And so here is heart, and here is diamond. And I can read this definition in the context of this to see what's happening. I meant to assign exactly one element of B. That is, I meant to assign either heart or diamond to each element of A. So in order to write down a function from A to B, I have to pick heart or diamond for each element of 1, 2, 3. The way I'm going to indicate that is by drawing an arrow from the element of A to the element of B I've picked to assign to it. And so this, as written, is a perfectly fine example of a function. Note I've indicated I'm calling this function f, and so if this was the function indeed, you would say, for example, that f of 2 is heart, and you would say that f of 3 was diamond. So the thing I want to emphasize here is, where is this exactly 1 going in this diagram? What is it that there's exactly 1 of? I've already told you this is a real function, so the fact that there are 2 arrows pointing at this 1 dot here, that's fine. But what is it that there needs to be exactly 1 of in terms of the arrows? And if you read it, it's for each element of A, there's exactly 1 element of B. So in fact, the thing that there is exactly 1 of is that there's exactly 1 arrow originating from each element of A. So please note the definition of function is highly asymmetric. That is, the set A and the set B have very different roles and very different expectations of them when it comes to what the definition of a function is. And that's why I'm constantly using asymmetric symbols, like the arrow points from A to B, these arrows point from an element of A to an element of B, and so on. Here are 3 more dot diagrams that correspond to things that may or may not be functions, going again from these same sets, that is from A equals 1, 2, 3 to B equals heart diamond. I've used the same orientation of the dots here. So, is each of these an acceptable function? Yes or no? So I want to draw your attention to a particular feature of each of these. In this example, there's an element of B that we did not use. In this example, there's an element of A that we did not use. And in this example, there's an element of A that we used twice. One of these 3 is a thing we're allowed. Namely, we're allowed to not use elements of B. That's fine. So this is a perfectly fine function. This is indeed the function that sends all of 1, 2, and 3 to diamond. And that's just fine, no problem there. Here, though, we do run into a problem. We have to use every element of A. That is part of our definition of a function. Namely, we're supposed to assign exactly 1 element of B to each element of A. And in fact, both of these pictures are violations of the exactly 1. They're just violations of the exactly 1 in different ways. In this case, instead of assigning exactly one element of B to each element of A, I assigned exactly one element to 1 and to 3, but to 2, I decided to assign 0 elements. And 0 is not, in fact, exactly 1. Here, the problem is almost exactly the same, except instead of deciding to assign 0 elements to 2, I decided to try assigning 2 elements to 2. But also, just as 0 is not exactly 1, 2 is not exactly 1. So both of these are not dot diagrams of functions. The recurring theme here, and this will continue to be the theme, is that the requirements of A to be a function are very strict, whereas the requirements for B are quite loose. I can use elements of B multiple times or 0 times. I must use every element of A exactly once. Or I must have exactly one arrow originating from every element of A, whichever way you want to think about it. Now that we've talked about functions in terms of dot diagrams, I want to go pick 3 functions from calculus and talk about how they work when we try and translate them to our new definition of function. I'll note it definitely doesn't just make sense straight off the bat to ask if these things are functions or not in our new definition, because our definition of a function involves a set A and a set B. So since no set A or B is defined here, we don't know. But we might ask, what is a reasonable set A and a reasonable set B to take? In single variable calculus, when you talked about functions, you were talking about inputs and outputs that were real numbers. So that is to say, you were probably talking about functions from R to R. And so one way, combining our various bits of notation to describe the function, whose domain and codomain are both the real numbers, and which takes the input x to the output x squared, is this. This in one line tells us everything that we need to know with our new definition of functions. It tells us the domain, the codomain, and what a hypothetical input x would map to, namely x squared. This is a perfectly reasonable interpretation of f of x equals x squared that we had above. Note this function already has some of the weird properties that we talked about when we talked about functions back in terms of our dot diagrams. Namely, there are outputs we don't use, right? For example, the output -7 is never used. And that's a-okay. We don't need to use all the outputs. And also, there are 2 inputs that map to the same number. In fact, there are lots of pairs of inputs that map to the same number. For example, -5 and 5 both map to 25. So, in other words, if you try and picture what the codomain of this looks like in terms of dot diagrams, I realize this is a stretch of imagination because, of course, in addition to 25 and -7, there are infinitely many other dots that I'm not depicting here. But in fact, no arrow goes to -7, because -7 is not something that gets mapped to by anything, because squaring something always gives you a non-negative number. But in fact, 2 different elements map to 25, namely both 5 and -5. These over here in A, among, again, infinitely many other things not depicted here. And both of these things, again, I just want to reiterate, are perfectly fine. This is a regular, ordinary function. No problems. What about g of x equals 1 over x? Can I do the same thing for g of x? Namely, can I just write down g from r to r, and it takes x to 1 over x? Is that a function in our sense of the definition? And sadly, our answer is no. This is not a function. What's wrong with it? And the answer is that g of 0 is undefined, because I can't divide 1 by 0. Again, if you picture what the dot diagram of this would look like, and I look in the input space, I have 0, but 0 doesn't map anywhere. There's no arrows originating from 0. Now, here is where 2 things in your mind might click together. Namely, you also used the word domain in calculus. It didn't mean the input set, because in calculus there was no input set or output set. But what did the word domain mean in calculus? The word domain in calculus meant the things you can put into the function and not get out undefined. And so, in fact, that actually tells us one way to fix this problem, which is instead of writing g from R to R, take what we would have in calculus called the domain. That is, take the set of elements that I can plug into 1 over x and not get undefined, which would happen to be the interval minus infinity to 0, union the interval from 0 to infinity. And we can take that and then leave the output being R, and then take x and map it to 1 over x. And this is a perfectly fine function. Just to note, stylistically, this is a perfectly acceptable way to write this set, but you might prefer to write this set as this, since that takes up a little bit less space. Namely, you're saying here, every real number except 0, that's the same thing this is communicating. So whichever of these you prefer is perfectly fine. I want to point out there's a different way to fix this problem that we had back here with x mapping to 1 over x not working. Namely, one way we could fix it was to change the domain by just removing the problem spots, or in this case, problem singular spot. Another way to fix it is to change the codomain. Namely, the problem is that if I just take x to 1 over x, g of 0 wants to be undefined. Well, I could just go ahead and put undefined into my codomain, and this will also work out just fine. Namely, we have the function which takes in whatever number you like, and then outputs 1 over that number, unless that number happens to be 0, in which case it dutifully tells you that 1 over 0 is undefined. And so here, we've chosen to actually just view undefined itself as a potential output of the function. And this is also a perfectly reasonable way to think of the function g of x equals 1 over x from calculus. So that explains what we could do with x squared. I gave you 2 different alternatives for what we can do with 1 over x. By the way, the more common choice is to think of this one, that is to just drop all the elements out of the domain that don't make sense. And so that's often called the natural domain of the function, which is just all the numbers where the output would make sense. Last up, let's look at this h of x equals the square root of 1 minus x squared. So let's try and do that for this function h. Namely, what's the natural domain here? And so the real question is, when am I allowed to take this square root? As an example, if you tried to put in 4 here, you would end up taking the square root of minus 15, which is not going to work. And so you have to figure out what numbers can I actually put in here. And in fact, the natural domain of this function is the closed interval from minus 1 to 1. These are the numbers that I'm allowed to put in, including minus 1 and 1, where I'll end up getting a square root I can actually take. Yet again, I'll point out there was also a very natural way we could have addressed this question by, instead of restricting the domain, extending the codomain. Namely, I just said, oh, well, you can't take the square root of minus 15, but maybe some of you thought, oh, sure you can, it's the square root of 15i, which is not a real number, so I cannot have the reals here, but it is a complex number, and so I could just as easily have written this as a function from the real numbers to the complex numbers. And that would have worked just as well. The complex numbers, remember, this is the set of all a plus bi, where a and b are real. Indeed, it turns out to be important that we could also extend this to a function from the complex numbers to the complex numbers. But we're not going to talk much more about the complex numbers in this class. But if you take, say, complex analysis, this will end up being an important component of the course. There's one more thing I wanted to point out to you in these examples, which actually was true all the way back in the first example when I talked about the map x goes to x squared. And that's that we have a lot of choices for what we could put here as r in the codomain. Namely, as I pointed out when we talked about this, I never used -7, or any other negative number. So I could just as easily have instead written f goes from r to the non-negative real numbers that takes x to x squared. And this would have been almost but not quite the same function. It's not literally the same function because the codomains are different. And part of a function is the domain and codomain. That is what sets you're using to define it. But in terms of its actual outputs, they're exactly the same. So in the same way that we'll often try and choose the largest possible domain, we'll also often try and choose the smallest possible codomain. And in fact, for any given function, we have a name for the smallest possible codomain. Namely, that's what we call the image. The way you should read this definition is that the image of f is all the outputs of f that are actually used. That is, if I plugged in every possible element of A to f, what are all the things in B that I would get out? In particular, note that by the definition of function, the image of f is always a subset of B. Note, this word image here is really describing the concept that in calculus we would have called the range of a function. Namely, the range of a function was all the possible outputs. And so the image now is just a word for all the possible outputs given a particular input set. As an example here, let's look at the function f from r to r that takes x to 1 over 1 plus x squared. Now, you might at first be concerned about whether this is really a function or not because I'm dividing. And so you might worry that I'm dividing by 0. However, if you look closer, what you'll actually see is that the denominator here is always strictly positive because of the x squared. And so in fact, we're never dividing by 0. Everything is okay. This function really is a function. So what is the image of this function? The image is the set of all the outputs that I get. And in terms of thinking about that, it might be helpful to picture what the graph of this looks like. Namely, the graph of this function looks like this little bump. In fact, this is often called the bump function. The y-intercept here is 0, 1, and there's a horizontal asymptote at 0. The image of this function, then, is collecting all the outputs I actually get. It's going to be a subset, really, of this r. And what is that subset going to be? It's going to be this half-open, half-closed interval, because the image is going to include 1, because f of 0 is 1, but exclude 0, because there's no input here that will give me an output of 0. If I go back to the earlier example where I had the function g from r minus 0 to r that took x to 1 over x, remember this is the one that was undefined at 0 because I can't divide it by 0, and I thought about what all the outputs here were, then again, if I picture the graph, I can probably convince myself that actually the image of this function is in fact also r minus 0. That is, I get out every number here as an output except for 0. Now, I want to note, calculating the image of a function in general can be very, very difficult. Just to show you what I mean by how difficult it can be, let's look at the function that I'm just going to uncreatively call f, whose inputs are 3 integers, that is an element of z cubed, a 3-tuple of integers. It's going to always output an integer, and the integer it's going to output is going to be x cubed plus y cubed plus z cubed. Now, when I ask about the image of this, I'm asking what are the outputs that I could get. So I could ask, for example, is 3 in the image of f? That is there an input to this function that would give me out 3? And I think if you think about it for not too long, you'll come to realize, yes, 3 is definitely in the image. 1, 1, 1. If I take f of that, I'll get 1 cubed plus 1 cubed plus 1 cubed. It'll be 3. So yes. As soon as I show you that there's some element in the domain that maps to something, it shows you it's in the image. And so I can just write that down in quantifiers. So just from the definition that we wrote down before, some element of B is in the image if and only if there's an element in the domain that maps to it. Okay, so let's do a few more of these. I'd encourage you to pause and think about these for yourself for a moment. Is 1 somehow in the image of this function? And the answer here is definitely yes. And so I could take, for example, f of 1, 0, 0. What about 10? Well, yeah. 1 cubed plus 1 cubed plus 2 cubed, that would be 10. So yes. Note as I do this question, what am I hoping the answer is? I'm really hoping the answer is yes, right? Because I would rather show a there exists statement is true than show the there exists statement is false. Because if it's true, I can just give you an example. What about 25? Here we have to be a bit more creative, but again, the answer is yes. Namely, if I take 3 cubed and add to it minus 1 cubed and minus 1 cubed, I'll get 25. Namely, the cube of a negative number is negative. So, in fact, actually answering this question can be a bit tricky, because I can actually take potentially some huge positive number and cancel it out with a huge negative number and still get a relatively small number. In fact, that's actually why determining what the image of this function is an open question. And when I last started teaching this course, whether 33 was in the image of this function or not was an open question. That is, no one knew if you could find cubes whose sum was 33. That is, could you find x, y, z integers whose cubes added to be 33? But fortunately, as of 2019, we no longer have to wonder whether 33 is in fact the sum of 3 integer cubes. 33 is the sum of 3 integer cubes. And you can see why, even though this is a problem that people have thought about for a while, it took a long time for someone to actually answer this question. If you'd like to make your mark on the world, and be mentioned in one of my videos for some future class, because you are the one who found the answer to this question, the next number is 114. So you will get mentioned on Wikipedia and whenever I teach this class in the future, if you successfully resolve whether or not it is possible to write 114 as the sum of 3 cubes. I'm going to wrap up this video here. In the next video, I'm going to go over more examples of functions and more questions about functions, so that you can get some more experience under your belt thinking about these things. But that's all for now. I'll see you next time.